It's really neat to see so many of you coming out tonight, hear about something pretty esoteric, so interactive graphics in R. So before I begin, so how many of you have used R before? Okay, that's cool. And how many of you have used GGplot, or at least heard of it? Okay, cool. So if you haven't heard of GGplot, unfortunately the first bit's going to be a little bit boring, because I'm not really going to talk about GGplot too much. I'm just going to say, kind of, why did I develop it? Why did I bother doing this? And then talk a little bit about what's going on with GGplot at the moment. I don't want to spend too much time on that, because I want to get to really the meat of the talk, which is where's GGplot 2 and in general, where are interactive graphics in R going? Okay, so why did I start developing GGplot 2? Well, this is sort of one of the motivating examples. So this is in 2004, when I was I was really into lattice. So I used to use lattice a lot. And this plot's kind of interesting because we've got 3 lines here, and you can see we've got a nice legend. But we've got this problem. So we've got 2H, 2M, and 12H. And what I wanted to do is say, well, let's have color, given to H and M, and the line type given to that number. And I tried and I tried and I tried, and I could never get lattice to do that. So that was sort of one of the first of my niggles. And there are a few other things, like why does the line panel not automatically order the point? So if any of your lattice users, you might remember the frustration of having what should be a nice line graph look like crazy squiggles. And there's a few other things. Why can you describe a histogram with a bin widths? Why, if you have an XY plot and set the panel to a box and whisker plot, why was that the same as a box and whisker plot? What was the real difference there? And also, why was it so hard to get different data sets on the same plot? And about the same time, I started reading The Grammar of Graphics by Lee Wilkinson. So how many of you have heard of this book? This is, I think, a really, really fantastic book in terms of laying out a sort of a deep underlying theory beneath graphics. And why do we need such a theory? Well, basically because it really helps us to think about graphics. And if we have a better theory underlying our software system, then we can make sure we can combine independent components more easily. So instead of having a whole lot of named graphics, what we're going to do is figure out what are the components that define a plot, how can we combine them together, and then create this idea of a grammar. So we can describe plots as combinations of their component parts rather than giving them some special name. So looking back, this made me realize I've actually been developing GGplot 2 for over 5 years now, with GGplot at least. So I started developing it in 2005 in version of R 2.2. So it's now R 2.13. So it's kind of scary that I've been developing it for 11 versions of R now. So I put a few milestones there. So it actually came out in April of 2006, and I announced it in July. So there was a GGplot before GGplot 2. I'll mention slightly why that was the case. And then the GGplot 2 mailing list didn't really get going to the end of 2008, and then the GGplot 2 book in 2009. So a few of the highlights. So in point 5 was when I transitioned from GGplot to GGplot 2, where I added this nice idea of adding plot components together with plus. It wasn't really until the next version when there was documentation, and the version after that allowed you to actually change the plot so you could have like white backgrounds for your journal needs. So I also looking back at my talks on GGplot 2, I noticed I made this rather prescient slide in 2006 when I said, hey, implementing the grammar was actually pretty easy. We've got this really nice, elegant underlying theory that makes it easy to kind of to program the big picture. But the hard stuff really is the details. So how do you figure out what the detail scales are? Where do you put tick marks? How do you allow the user to control the plot? And sort of interestingly, some other milestones. So remembering the first version of GGplot 2 came out in April 2006. So in that month, I got my first question about how do you put 2 plots on the same page, which recurs today. why are the breaks and why are the tick marks and the axes in such bad positions, and then a month later, how do you get rid of the grey background? So, and if any of you subscribe to the GGplot 2 mailing list, these questions continue 5 years later. So, it's so surprising that really the big picture stuff, once you have this nice, elegant underlying theory, the big picture stuff's actually pretty easy. But as with many things, the devil's in the details. Getting really, really good, polished visualizations requires a lot of work tweaking these small details. Okay, so what's going on at the moment? Well, one thing I'm I just love about GGplot 2 is the community. So we've got a fantastic mailing list. It's about 1,500 members, 9,000 messages, which scarily, I've written 1,000 of those. And unlike our help, it's generally pretty friendly. You're not going to get anyone calling you a moron or similar. If you don't like mailing lists, Stack Overflow is also a pretty good place to ask questions. I hardly answer any GGplot 2 questions on Stack Overflow anymore. There's a great resource of people there who can help you if you get stuck. And even more importantly, for my sake, is that in the last version, about half the fixes and features were contributed by a community member, Takahashi Koshiki. So it's really great that sort of GGplot is migrating beyond me. You don't have to worry so much about me getting hit by a Caltrain on the way home and no more development happening. So what I've been trying to do this summer, really, GGplot 2 is way, way too complicated. In fact, I don't really understand how a lot of it works myself anymore, and so it's really difficult for me to develop it because I don't know how it works, and it's even harder for people who never understood how it worked to do anything. So also GGplot 2, well, GGplot was the second R package I wrote. I've now written about 30, so I know a lot more about R package development. So what I've been doing this summer, or starting on this summer, is trying to break it up into simpler pieces that people writing other visualization systems in R can use. It doesn't matter what sort of plotting system you use, it's always hard to come up with good scales and automatic tick marks. So rather than every person, Lattice and GGplot 2 and GGplot and other derivative plotting systems, rather than everyone having to do that hard work, why not pull out all of my hard work into separate packages so you can use the same ideas without having to buy into the whole GGplot 2 philosophy. So there's also a whole lot of other things that go along with that. So I'm making it easier. I made some bad decisions very early on to use Proto instead of S3. It now has one documentation, Roxygen, instead of two entirely separate homegrown documentation systems I wrote. It's going to have some tests in the next version, which is great for me, because now when I fix one bug, I'm not going to create another bug. And I've had a few cases where, in one version I fix a bug, and it creates a new bug, and then in the next version I fix that bug and it recreates the original bug, and it takes me a little while to figure out that I'm going around in circles. I'm also working with Revolution Analytics to get GGplot 2 working with big data, so this is pretty exciting. So the idea at the end of this, if you've got 120 gigs of data, it should be trivial to use GGplot 2 with this. So this is going to be open source, focused work initially on working with Revolution Analytics, high performance data structures, but a lot of the back-end work is going to help make GGplot 2 faster for all sorts of other data as well. Because unfortunately, that's really, I think, the biggest downside of GGplot 2 at the moment is it's just dog slow sometimes. So the other thing I'm really trying to do is kind of, my job, I'm not a software developer, I'm an academic. My job is to create research and create new things. It's not to make nicely developed R packages. But I'm always kind of torn between these two perspectives, one of kind of pleasing my existing users, being a good software developer, and being a good academic and producing things that really push things forward rather than execute existing things nicely. So I'm trying to figure out how to fund maybe a full-time GGplot 2 programmer and to really help others get their R skills up to a place where they can start developing my packages. So or how at least, well, not just my packages, but generally how can we get kind of more skilled programmers in the R community so that when, instead of doing the same things again and again badly, we can really figure out what are good ways of developing packages so we can be creating new things as well. So, you know, if you have a few $1 million lying around, send me an email and I'll be happy to help you spend it. Okay. So now I want to talk about the fun stuff, so which is the future. So hopefully, if you don't know anything about R or GGplot 2, now's the time to wake up again. But to talk about the future, really, I do have to go back to the past again. And what I want to do is compare two systems for doing research in statistical graphics. So one is Orion 1, which John McDonald used in his thesis in 1981, and my laptop in 2011. So about 30 years difference. So Orion 1 cost about $250,000. My laptop was about $2,000. So, you know, the cost of computers has come down 100-fold. He had an 8 megahertz computer. My laptop's 2 gigahertz, so it's about 300 times faster. He had 128 kilobytes of memory. I've got 4 gigabytes, so 30,000 times as much memory. But if we look at the screen, actually, we come out about even. So we can cheat things a little bit if we add on. I've got a 30-inch monitor, so if we add that into the picture, the cost goes up a little bit, and I've got a few more pixels than he had 30 years ago. But I think this is really striking. In the last 30 years, speed has grown incredibly. Memory, you know, both memory and disk space have increased incredibly, but we're basically at the same number of pixels as we had back then, by and large. So what can we do? What does that mean for graphics? And, you know, even though our data is getting bigger, our screens are not. And even if our screens were getting bigger, you know, it gets to some point where if you have to do your analysis on a giant wall, it's not quite as convenient as doing it on your laptop. So what we really need is interactivity. So instead of displaying the same data, we need ways that we can really, really quickly change what we're displaying, either change the data, the way we're displaying data, or change the way that the raw data is summarized. So at some level, whatever the size of our data set, it always has to come. We can never display more data than we have pixels on the screen. So we always have to aggregate. It doesn't matter if we've got 100,000 points or 100 billion points. If we want to visualize it, we need to be able to aggregate it, show it on the screen, and we need to be able to very rapidly change what we're saying. So what I'm going to do next is show off 4 little applications I've written. These are all written in R, just showing sort of where we're trying to go in terms of interactivity. Oops, that was the wrong one, don't worry. So this is a little applet that I wrote after I saw this visualization online. Have any of you seen this before? So it's really interesting. So and slightly creepy. So the IRS releases this data. The IRS are basically the only people in the US who know where you lived last year and where you live this year. So they release this information into the public about where people are moving. So what this is a map of the US. I've clicked Story County, Iowa, which I'll talk about shortly. And what it's showing is where people migrated from and to. So I think this is really neat data, but if we pick someone a little bit bigger, we can see that this representation doesn't work so well. It's kind of hard to see what's going on here. So I really like this visualization, this idea, how can we see where people are moving around the US, but I didn't like this representation so much. So here's my version. So hopefully this looks familiar to all of you. We've got a map of the United States, and it's broken down by county. So this is all written in R, and what I'm doing is I hover around. You can see the name of the county in the bottom left. So what I'm going to do is click on Story County, Iowa. So this is the home of Iowa State, where I did my PhD. And what it's showing is the gray dots show where people have moved from to move into Story County, and the red dots show when they leave Story County, where do they go to. So I think this tells a pretty interesting story, because when we look, who is moving to Ames, Iowa? Where are they coming from? Well, basically people come from all over Iowa. And then where do they go? Well, if you go to Des Moines, this is Kansas City, New York, Denver, Houston, the Bay Area. So people move to Story City from Iowa, to Story County from Iowa, and then when they leave, they go to big cities. So we can actually follow this. So this is me. I moved to Houston next. So when we move to a bigger city, obviously we've got more data, right? This is it only shows a minimum of 10 people moving from one county to another. So when we move to a bigger city, when we've got millions of people, we've got a much higher proportion of people moving around. So we can see, a lot of people are moving to Houston from the northeast. Interestingly, people seem to be leaving, when they leave Texas, they seem to leave for outlying areas. So these are kind of some of these big red dots are outlying suburbs. So the size of the dot is proportional to the number of people. I don't have a legend here, mainly because legends are basically the hardest part of any graphic system to write, so they're still lacking a little bit here. But one day, hopefully. So we can also follow, so if we see, we can look at so I think we're in Santa Clara County, right? So you can see where people are going from there as well. Again, coming from the northeast, it seems, and then they move out further north or into outlying suburbs. So, this is the sort of, I really like this example because it's a pretty big data set. Let's see if I remember what these things are. Flow, I think. So it's got about 100,000 observations. So there's 2,000 counties in the US. So it's from every county to every other county. But obviously there are a lot of counties, if you kind of pick somewhere out here, there's, there might be like 5 people living in that county anyway, and they all left. So there's also sort of an interesting thing here, which is a problem with a lot of maps, is that sort of county size tends to be roughly inversely proportional to the population. So the bigger the population tends to be the smaller the county, which is a problem whenever you're trying to represent data on the map, because you don't really want to draw attention to this region out here where it's basically the Rockies and no one lives, whereas over here in the northeast, you've got millions and millions of people, but the counties are really small. It's really hard to see that. It's also interesting. The other thing I love with these maps is you can see, pretty sure this is the Mississippi along here, right? We're not really seeing the Mississippi, we're seeing it how it affects county borders. But that's kind of an aside. The other thing is, so I've now lived in the 2 states that have the highest number of counties in the US, both of which the counties were designed so that you could ride your horse to the county capital in a day. That, again, as a side. Okay, so that was sort of one little example. It's really in some sense, it's a completely novel visualization, right? It's not a scatter plot, it's not a line chart, it's something new. The interaction is specific for this problem. Okay, the next thing I want to show, oops, and we have to switch. So again, this is development level software, so we have to do a little bit of jumping through hoops. So how many of you have heard of GGobi? Anyone? A few? Okay, so I'll talk a little bit more about this shortly. I sourced the wrong file in there. But one thing, the direction where GGobi is going, GGobi was a software for interactive and dynamic graphics. We're basically rewriting it all in R. So let me reduce the dimensionality of this a little bit. Okay, how many people have heard of a grand tour? Okay, even smaller. So the idea of a grand tour is really simple, right? If you want to figure out the shape of a 3D object, what you do is you look at it from different angles. So what I've got here is a 3D data set, right? I've got 3 variables, and I'm just randomly rotating it around, looking at it from different projections. So if you watch this for a while, and I can add on some color. If you watch this for a while, you should be able to build up a pretty good mental model of this shape. So even though, there's no 3D here, right? Everything's into 2D, you're just seeing a sequence of projections into 2D, and your brain stitches this up into 3D. So the neat the basic idea of the grand tour is that the mathematics is exactly the same for 3D as it is for 4D. So now we have a 4-dimensional data set. We're randomly rotating it around and looking at it from different directions. So one thing to when you're looking at plots like this, no longer it's not just the position of their points that might tell you if they're clustered together, but it's also their relative motion. So if points are moving together, then they'll seem to belong to a group together. And if it generalizes to 4D, then, well, we can go all the way up to 9D if we want. So you might see if you watch this for a while that, I've colored these 3 regions, 3 different colors. You can see pretty quickly, right, that we can separate these out. There does seem to be some separation between these clusters. They're not intertwined. So that might give us some hope that if we're going to try and predict the cluster membership from the data, that we might be able to succeed if we pick the right method. And in this data set, you can't see that just by looking at individual 2D projections. That's just not visible in the data. So there's a few other things we can do. So the grand tour just randomly wanders around, and as the size of the data, this number of dimensions gets bigger and bigger. It's going to take longer and longer before you see anything interesting. So what we could do, instead of doing a grand tour where we're randomly moving around, we could use a guided tour. So the idea of the guided tour, well, I didn't pick a very good one. So instead of randomly going around, it's going to tour with intent. It's going to try and find projections. The index I'm using is going to find projections where the clusters are separated. So you can see it's taking longer and longer. It's doing a stochastic kind of search to find these projections. And here's one where it's done a pretty good job of separating out those clusters, right? And then if we really wanted to, we could go ahead and interpret this. We can read off these guys here are the axes projected down the data space. In the same way, if I'm rotating a 3D object around, you can see the projection of the axes on 2D. The same idea here. We're looking at the shadow of those axes in 2 dimensions. This is it's a little bit mind-boggling at first, but you can actually use this idea to get a fairly good feel for 4-dimensional and higher shapes, even though our brains are not particularly well suited for the task. So what else? So this is all, written in R again. This is a little bit inelegant because I'm using, as I'll talk about shortly, Qt to draw this graphics canvas and GTK to draw this GUI. So we've kind of got 2 completely different graphic systems, GUI systems going on, but we've got all sort of our usual sliders. We can make the points big and faint if we want, or whatever. So that's sort of so. The thing that's really amazing about this is now actually faster than GGobi. So GGobi was software purely written in C, and now in R, if we've got the right primitives, if we've got the right functions in R written in C, we've written them really well, that means we can now actually write high-performance graphics just using R code. And I'll come back to that thought in a little bit. So this is our joint work with Bay, who might be in the room now. I don't know if she came or not, but she did sign up. Okay, so another thing I want to show, another kind of custom visualization I created. So I always find myself kind of going down these rabbit holes, so I'm trying to figure out how I can make GGplot 2 faster. And so if I'm going to make it faster, I need to first understand where it's slow. And well, there aren't any particularly good tools in R for that. There's there's good tools for capturing what's going on, but for visualizing and exploring it, there aren't. So this is a little tool my grad student whipped up for me. So what we're looking at here is a profiling data. So you can see down here, down the bottom, this is the function I called the print function, and the print function called qplot and some other functions. So this is a way of exploring what functions are taking up the most time in GGplot 2. So you can kind of see, so this is the bottom level. That function then calls other functions, which call other functions, which call other functions, all the way up to about 20 levels down. And you can see the width of the function is how long it takes to run. So one problem with this kind of display, if we're doing this in our graphics are vector graphics, which is normally good, right? It means you can put them out to a PDF and you can kind of zoom in infinitely and gives you all sorts of nice things. The problem is that it doesn't give you access to kind of the pixel size. It's too far abstracted from the actual screen. And so one nice thing you can see here, which is extremely difficult to do in our graphics, is when the boxes are big enough to put the function name in, the function name appears. There's a few other features. So whenever I hover over a function, it's going to tell me the name in the top left corner, and it's also going to highlight all of the other calls of that function in here. And then finally I can click in, so I can click in here and zoom in and find out what's taking up the most time. So this is kind of interesting. You can see, so this building process is where ggplot 2 basically collects all the data, scales it, transforms it, creates a nice data structure. Then GGplot grob basically takes that nice data structure and turns it into a whole lot of graphics objects, and then grid.draw draws those graphics objects. So this is really useful from my perspective because I can see where's the time going. Well, I mean, grid's out of my control, so I can't really modify what's going on here. So that suggests if I want to make this plot faster, it's about equally between the building up the data structures and building up the graphical objects. And, you know, I can continue to zoom in and sort of find out in other ways what's going on. So this is really neat because it allows me to create this. This is so neat because it allows me to understand what's going on in profiling data much, much better than I ever could before. And I've kind of been dreaming about this tool for like the past 5 years, and now the QTPaint, which I'll talk about a little bit, is really mature enough that you can whip something up like this in a couple of days. So it's still a long way. You know, my eventual goal is we want to be able to whip something like this up in a couple of minutes, right? Like in the same way that with GGplot 2, you can create an entirely new graphic in a few minutes. We want to eventually be able to do the same thing with interactive graphics. So by figuring out what the primitives of interactive graphics are, thinking about how we can combine them, we can create new graphics in a much, much easier way. And in my mind, that really, if you're using graphics for data analysis, the speed of iteration is one of the most important things. You know, if it takes you 15 hours to come up with your graphic, then you're going to be really, really, really unwilling to change it. And to me, that's when I look at sort of infographics on the web, that's the one thing I always wonder, right? You've spent so much time making this beautiful thing, and I can see you've spent like days and days and days and days doing this, but how do you know that's the best view of your data? And unless you can really look at many, many different views of the data very, very quickly, the chances are you're going to end up with something suboptimal. So I certainly don't, you know, I think it's great when you're trying to communicate, you do need to spend a lot of time polishing a graphic, but you need to make sure you're polishing the right graphic, not just the first one that came to mind. Okay, so one last interactive example. And this is joint work with Yihui, Heike Dai, and the entire Iowa State Stat Graphics group. Okay. So I'm going to have to apologize for this data set, which is really awful. It's the crimes. Oops, trying to move the wrong window there. It's the crimes data set in R, so it's really awful. So just ignore the data and focus on the idea here. So what I've done is I've drawn 3 plots. I've got a map of the US. So I've colored the states according to their population. So you can see here's California with lots of people. Again, we've got a legend here, but you might notice that perhaps we haven't picked the breaks as well as we might. We've got a scatter plot here, which shows the population on the x-axis and the log 10 proportion of robberies per population, and here I've got a parallel coordinates of all of these different attributes. So the neat things about these graphics is that they're linked together. So if I click on California here, I'm going to see that in the scatter plot. It's the biggest. It's got a pretty high rate of robbery, and I can see that in the parallel coordinates plot as well. Or I can go to the parallel coordinates plot, select some points there that look interesting to me, and see where they are on the map and where they are on the scatter plot. So this idea of linked brushing is really, really important. If you want to figure out what the multivariate relationships are in your data, it really, really helps to link together multiple views, trying to put everything onto a single plot. So I guess how many people are familiar with the parallel coordinates plot? Okay, so the idea, I should explain it briefly then. The idea is, so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 variables in my data set. So it's 10-dimensional. What I've got here is each line represents an observation in the original data set, and my variables are now going across. So this is the population variable, the violent variable, the murder variable, rape, robbery, assault, and so on. And the lines connect the value for the observation across all of those variables. So I'm not a big fan of parallel coordinates because the reason I think they're difficult to read is because they try and put everything on one plot. So typically, what I think it's easier to work with is kind of simple plots that you then join together. So the idea, it's kind of easier to work with, say, a couple of scatter plots paired together. With 2 scatter plots together, we can get some idea of the 4-dimensional shape of the data, and here we can connect it to a spatial view of the data as well. So let's see if I can resize this. Here we go. So one thing I can do is we can kind of brush down. So these are the states with the highest robbery, and moving down lower and lower. So can you see any spatial pattern there? It looks like there's a bit of one, right? That maybe robbery. Get fewer robberies the colder it gets, perhaps. And so on. So for this example in particular, I just wanted to show the code that creates that briefly. And here it is. So we've got basically 30 lines of R code that creates those plots. So this really is what the future of GGplot is of GGobi really is at the moment. So this package is called cranvas. I'll talk a little bit more about it shortly. But the idea is we want to create plots that know how to communicate with one another. And the thing that really is amazing is that by and large, all of this communication is done in pure R code. I'll talk about the exceptions. So you can see here, I've loaded up my states data, I've converted into a Q data frame. Kind of forget what the Q stands for, but basically that turns it into a mutable data frame. So a data frame that you can actually modify and that other functions can listen to and see what's changing. So obviously really important if you want to link together 2 plots, you need some way of communicating between them. Then I create a map of that, get the crime work, do a little bit of processing on the crimes data, do the same thing, convert it to this Q data, which allows us to link the different plots together. I create a parallel coordinates plot, then I specify how do I want to link the different data sets together. I've got a data set that is the map borders, the county, the states, and I've got a data set that's crimes. How do I describe how to match those together? How do those link up? And then finally, I do that scatter plot. So really what we're working towards is being really easy to make sort of interactive graphics in R. So this project, this Cranvas project, is really the future of GGobi rather than the future of GGplot. So the emphasis on this on Cranvas is recreating kind of the most common plots in a way that's really efficient. So it's more like kind of base graphics or lattice graphics. It doesn't have this idea that there's sort of some deep theory. It doesn't really make it possible for us to create our own interactive graphics. So I can show some of the other code. So the code for the first one, we're looking at migration. So it's about 120 lines of R code. Right, so if you, I don't know, I can't really show you, there's nothing going on behind the curtain, but hopefully you can see this all looks like R code, right? I'm just writing it in R. I didn't need to learn C or Java or anything else. I can now start to write interactive graphics just using what I know about R code. Okay, so those are kind of the 4 demos. That's probably the the highlight of my talk. I just want to talk a little bit more now about what's going on behind the scenes there. So how, instead of just relying on my interactive graphics, how can you go out and create your own in R? So there are basically there's two key packages here and a couple of other ones that we've been working on. So QTPaint provides us with a high-performance graphics canvas. So this is backed by OpenGL. It allows us to really, really rapidly push pixels onto the screen. So it's comes from the Qt library, it uses OpenGL, so it's hardware accelerated, it's really, really, really fast. On the other hand, for the linking, we've got this plumbr package, which gives us mutable data frames. So in R, basically, whenever you think you're modifying something, you're not. You're actually making a copy and modifying that. So obviously, that's a real problem if you're trying to communicate between different plots, because nothing ever changes. You're just creating copies that get updated. So we need some kind of data structure that allows us to communicate between different plots. In two other packages, so the tour package, you've really got to roll that R. There's two R's there. Implements basically the ideas behind the grand tour from GGobi and pure R code. Again, sort of surprisingly, it actually turns out a lot of these, you can implement these things. Not only they're quicker to program in R, but they turn out to be actually quicker than the equivalent C code, because the C code in GGobi was written by a bunch of interactive graphics researchers. The C code for like matrix manipulation in R was written by people who really know how to write fast code. So that sort of moving up to a higher level language doesn't have as many performance penalties as you might think. It can be really, really fast. And then, as I mentioned before, the scales package is slowly extracting the scale-related code out of GGplot 2, so it should in future be easier to draw legends on these plots, because it can leverage a lot of the code I've already written for GGplot 2, the really hard stuff in interactive graphics, like figuring out where your tick marks should go. Okay, so the QTPaint package is written by Michael Lawrence and Depai and Saka, the lattice guy. So there's two components to this. So qtbase basically provides a complete wrapper to Qt. Qt is a kind of yet another set of libraries for writing GUIs. We've chosen to go with Qt because it makes a nice wrapper around OpenGL, a nice way to access the really high-performance stuff that your graphics card can do without having to worry too much about the fact that there's like 200 different graphics cards and they each do things slightly differently. So QTbase is very general. You can use that to write all sorts of GUIs. Anything you could do with Qt and C++, you can now do in R. And then QTPaint's built on top of that. It's basically a sort of a next-generation graphics canvas for R. So instead of relying on the old, slow R graphics devices, which, sort of an illustration is if we just want to stick a million, I guess. I generate a million random numbers and I plot them. We're sitting here waiting for something would be this long. We're sitting here waiting, right? But if we want to be able to do interactive graphics, if we want to be able to animate things, we need to be able to we need to be doing things so we can update the screen 30 times a second. Right, we need to be taking on the order of 30 milliseconds, not as we did here, 25 seconds. So, one component of that is doing, this is obviously a really uninformative plot. We need to do better aggregation, right? We need to do some statistical computation. We need to think about what sort of display do we want here? How do we want to display that 2D density? But also, we just need some better way of pushing pixels up onto the screen. So it's as fast as possible. It's not a bottleneck for us anymore. So basically, these are the packages that do all the hard stuff. They're all written in C. If you build on top of these, you don't need to know anything about C. You can just use pure R to write fast graphics. So currently, it's painful to use these packages. So you can only use them on the Mac and some variants of Linux, and requires like 8 hours of compiling stuff typically, which is not a really pleasant user experience, but we've kind of learned from the past. And really what we want, the aim, and hopefully we'll be there by the end of summer, is that you'll just be able to say in R, install.packages QTPaint. You don't need to install anything outside of R. It just installs everything you need, and you're up and running with interactive graphics just like that. So I think all going well, that's probably going to make one of the largest packages out there, because you have to download about 20 meg of system libraries and stuff. And unfortunately, it's going to have to be on Bioconductor rather than CRAN because of a disagreement over what GPL2 means in terms of distributing source. But all going well, we will have this available. For interactive graphics to take off, for people to use this, we absolutely know that it has to be super, super simple to install, and that's really what we're pushing for. So there's still a few challenges we're trying to resolve, both at the kind of the programming level and also the what's the best way to write interactive graphics in R? How can we help people who are experienced R programs get up to speed on this really quickly? There's some really fundamental changes that if you're used to working in R, where all of your objects are immutable, you can never modify them. The object system is completely different to what you might be used to from Java or C# or whatever. And then all of a sudden, you've got to sort of start thinking about how mutable objects work again, how do objects work in Java and C#, and there's sort of a little bit of a mismatch in terms of thinking in an R way and thinking in a C++ way that we're still trying to resolve. Also, currently, you need to be able to be happy reading documentation written for C++ and then translating that into the original R, which is not so easy. And then, despite the fact that I said that Qt is supposed to kind of abstract over these differences in graphics cards, we're still having a few problems with that. So unfortunately, it's kind of a little bit, really depends on what version of what graphics card you currently have installed on your computer, whether it will work or not. But we're fairly hopeful that this will all get ironed out, and again, it'll just be easy to kind of get up and going, at least on a relatively modern computer with a modern graphics card. So with kind of that in place, where do we want to go in the future? And again, it's sort of useful to look at what people have done in the past. And I think for interactive graphics tools, it's really useful to kind of break them down along some continuum of high level and low level. So the idea of kind of low level systems is they should be flexible. You want to work with code. You're going to be writing a lot of code. You're thinking about things at the sort of a graphics level, and they tend to be kind of more research focused. So you don't expect that people are going to be picking up these low-level things and using them, for data analysis, or most R users aren't interested in that kind of thing. So at this kind of level, what I just talked about, QTPaint, so processing, how many people have heard of that? That's sort of a Java-based web visualization. That's sort of a massive generalization, but that's pretty low level as well. You're really thinking about this as the pixels on the screen kind of level. Protoviz moves a little bit further up the abstraction. It's written in Java, script, sort of starts to think a bit about having components that you can combine together. And as we move across, we kind of move up into systems that start to have more pre-built components. So GGobi, you can't create a new graphic in GGobi, a new type of graphics. You can just use the existing ones that are built in. And then as we move further and further up, we get more and more polished GUIs. So things like Tableau or Spotfire, Mondrian or Manet. These are really targeted towards specific types of data analysis. So these typically you work with these with a GUI. You're thinking about visualizing data. You're not thinking about what the pixels on the screen are going to be. You're using them for data analysis. These are sort of the really high level things. So, and then in the cranvas package, which I forgot to include, would be sort of somewhere up here. Well, I guess it'd be more like somewhere down here. Right, so you can use these kind of built-in graphics, you can connect them in new ways, but you can't use the Cranvas package to come up with fundamentally new types of graphics. So personally, what I'm really interested in is basically the grammar of interactive graphics. So how can we extend the ideas of GGplot, thinking about what are the fundamental components of a graphic, now thinking about what are the fundamental components of an interactive graphic, and how can we pull out those building blocks so that we can combine them quickly and easy to create new types of interactive graphics. So, currently, with QTPaint, it might take me, 2 or 3 days to design an interactive graphic. Again, that's too long. It really hampers experimentation. I've got no idea whether that graphic I've just created is going to be successful or not. I need to be able to move to something where I can start iterating graphics in hours or minutes, so I can really tailor the graphic for the task that I want to accomplish. So check back in 5 to 10 years and I'll let you know how that's going. So unfortunately, it really is it's a much bigger challenge than just figuring out static graphics, because there's just so much more. What are the possible things you can do to a graphic? There's just such a huge variety of things. What can you do with a keyboard? What can you do with a mouse? Clicking and dragging, thinking about higher levels, what's really going on there, and how can we think of some way to decompose that in a way that we get building blocks that can be joined together orthogonally to create something new. So that basically concludes my talk. I just wanted to quickly say, so I'm also really, really interested in the process of data analysis. So what do you do when you're kind of getting data in and trying to get understanding and insight? So a lot of what generally my research is in is how can we make data analysis easier? And that sort of naturally raises the question, well, what is data analysis? What are we doing when we do data analysis? And, I've created tools that work well for what I do when I think I'm doing data analysis. Other people seem to like them, but I'm really interested in any perspectives you might have in terms of what are you doing in data analysis? What are you struggling with, particularly in the context of R? What do you find easy in R? What do you find hard in R? But also generally in any programming language, what are the things that you're kind of struggling with when you're trying to do a data analysis? Or again, if you want to find out anything more about the packages I've mentioned, so they really are at the sort of the alpha or beta stage at the moment, but all the code is available online. We have some fairly reliable ways of getting them all installed and working on your computer. So if you are interested in experimenting and you're prepared to put a little bit of time into it, that's definitely possible, and please feel free to shoot me an email about that. And then finally, if you've got internships or jobs for my students, I'm trying to churn out students who are kind of understand both the statistics and they have the computational tools to deal with large data. So if you're looking for undergrads or grads who can do that, I'm also really interested to hear from you. So thank you.
Does people have questions?
Could you comment, please, on any approaches that you find? I'm interested in real-time streaming data, and that presents a big challenge because you can represent it by consecutive snapshots, or you could also embed into the visualization characteristics of something. For instance, the variability or the strength of a trend or other things. So if you're trying to identify trends among a lot of alternative objects as early as possible, so that's an example of something. I just wondered what you find.
Yeah, so streaming data is not something that I've ever really worked with. My main recommendation is Simon Urbanek at AT&T, who's also developed a lot of interactive graphics tools and stuff for R. I think he would be the person to kind of watch in terms of what's going on there. I know he's written some papers on kind of approaches to streaming data and dealing with it in R. He's involved at AT&T on the UseR team, so they have huge quantities of data coming in, and they seem to be Simon Urbanek. If you Google, I think iPlots is one of his R packages for interactive graphics. So I think...
If people have questions, you probably compute.
We might want to move that a little closer.
I mean, if people have questions, just come here to ask, sorry, because we're doing recording.
This is really awkward. So my question is, what are your plans for making this interactive stuff work with the web?
Yeah, that's a good question. So I don't know quite how to answer it. In some ways, that's sort of not the audience I'm aiming for. So in some ways, I'm primarily interested in exploratory graphics, so graphics that you're doing for yourself as a way of understanding the data. So the exploratory graphics, you go through hundreds of them, you throw most of them out, a few of them give you some insight of the data, and a few you then keep and polish and make available and turn into expository graphics, which help other people understand what's going on. So for exploratory graphics, I'm just not sure how useful the web is at this point. So I'm kind of following the WebGL stuff and HTML5 and so on, but it's still, I think, not quite there. So you're always going to need some kind of data backend, data analysis backend that's going to do all the statistical transformation. And it's points I've thought about. How can I write GGplot 2 in JavaScript? And then I look and see, whenever I look at a graphic, any non-trivial graphic I do typically has something horrendously statistical in it, like a nice lowest smooth curve through the data or a density estimate. And when thinking about re-implementing all that in another programming language just seems kind of pointless. So for exploratory graphics, I don't know, I'm not convinced that the web is ever going to be right for that. Particularly because you want to have these sort of multiple windows that are all linked together. For expository graphics, obviously it's great. It's great to be able to think about what's the sort of limited interaction I can provide so that people have a little bit of freedom to explore the data, but I've constrained them in some way. And I think the New York Times, their interactive graphics are a fantastic illustration of that. You get a little bit of freedom to explore the data. It's really interesting, but it's not enough rope to hang yourself. You can't kind of get to an uninteresting place, or it's not really confusing. You don't have 300 GUI menus to choose from. So, I don't know, I mean, really what I'm aiming for is exploratory graphics. Maybe the stuff I do will eventually become expository, but it's probably enough work for me figuring out how to do exploratory graphics. But I mean, I think it's really, really interesting, and it's really, really important, and I think we're seeing some stuff in R in terms of exporting out proto-viz graphics and things that I think that's really neat, but it's just not something that I'm working on.
I had a question about how the interactive graphics works with the actual database and manipulations of the database. And what I'm thinking of is you have a set of data and you make these graphics, you do several things with them, and you have a routine. And then you get more data later on, and you include more data which may change the dimensionality, may change. So I just want to know, are these two completely separated issues within R and all these packages, or do you have to work to sort of put new data in?
Yeah, so I mean, in some sense, that's the kind of the idea of this plumbr package, that it kind of provides a data frame that you can sort of modify, and all the plots will find out about. So of course, making sure that your interactive graphics know what to do when the data changes. I mean, I think that's the real challenge. So when you get more data, what should you do with it? And also, none of the examples I showed here really do much in terms of modifying the data, right? That's a really important interactivity you want, is be able to look at different subsets of the data or aggregate it in different ways. Particularly when you've got very large data, you want this idea, you want to get this sort of a broad overview and be able to zoom in and aggregate more finely as you sort of dig into the details. And that's just something I haven't had time to look at yet.
Two questions. First of all, with the grammar of interactive graphics, it's obviously much more, not as defined. How is the project dealing with the fact that the language for describing interactive graphics isn't as clearly defined as GGplot 2? And secondly, what's the best graphics card to use with this stuff if I was buying a new graphics card for a laptop?
So the second question's easy to answer. I've got no idea. But anything modern should work well, and presumably the bigger the numbers are, the faster it'll be. I can't really offer anything more specific than that. In terms of kind of figuring out what the interactive grammar should be, I mean, you're kind of seeing what I'm doing. I mean, the way that I'm going to slowly working my way there is by kind of doing lots of these little interactive graphics and thinking about, what are the commonalities between them. So obviously the interactive grammar will have to build on the static grammar, but it also needs to think about, well, what can change? And, I sort of see that basically you can change two things. You can either change the data or you can change the way it's displayed. So that's not a particularly brilliant insight, but in terms of thinking about like a GGplot 2 graphic, it's are you modifying the underlying data set, or are you kind of modifying the parameters where it's transformed, or the scales and so on, and then thinking about how you can kind of map those to ways you interact with the computer, whether it's a mouse or a keyboard or whatever, and how you can kind of control those. So there's sort of all sorts of really simple things, in terms of thinking about, I'm going to do a histogram, I can make a slider that is the bin width, right? I mean, that's sort of a really kind of a trivial thing. It's often useful, but I mean, that sort of seems a fairly shallow type of interactivity to me. I mean, you want more than the kind of Excel interactivity where you can click some spin bars and your graph changes. So I don't really know yet. I haven't kind of done enough experimentation, and a lot of these, I don't know if has anyone heard of Quail or Orca? These are kind of real statistical graphics research kind of tools. They have some interesting ideas, but in some ways they develop their own grammar of interactive graphics. But when you compare them to what people are doing and with interactive graphics on the web, there's just this huge range of things that I think are really, really useful for data analysis, but statisticians have never really thought about in the past. So yeah, it's sort of in the very early exploration stages at the moment.
So you did a wonderful job for those who were using to lattice. You transformed GGobi, you revolutionized. Do you think about the next thing, RGL, for example, to be included in your packages or be working with improvements?
Yeah, so RGL is interesting because RGL is basically nice 3D graphics in R. Basically, I kind of think 3D graphics for statistical data are useless. It's a fairly strong claim. I think there's only really two interesting cases, so 2D and ND. So the problem with 3D is, when we're looking, the way our brain constructs a 3D reality is, kind of 2% using actual parallax physical measurements with our eyes, and, it's like 95% heuristics, like, things that are further away are smaller than things that are close, and things that are close block things that are further away. So, and that works really, really well when we have some kind of underlying physical object that we're really good at we can see stuff on screen and we can figure out, what are the 3D contours of that. But when we start moving into abstract data, those heuristics they break down and they don't really work. So I've done a little bit of experimentation. I don't know if I might be able to quickly remember how to do this. This is another thing in the tour package. So if anyone's bought, let me just check. So if anyone has bought their 3D glasses, this is the time to get them out. So I've done some experimentation. I mean, this is a tour again, except now we're projecting first into 3 dimensions, and then we're using stereographic projections of 2D, and we're displaying that with different colors. We can do, so that's sort of one way that if we had 3D glasses, you know, that tricks your eyes. Or the other thing we can do is just use a whole lot of those heuristics. So again, I'm displaying in projecting into 3D, and then I'm using, to show depth, I'm using 3 things. I'm using the size, you know, close things are bigger. I'm using things being in front of other things, and I'm using kind of fading out the color when they're in the distance, sort of things get foggier and blurry in the distance. So this does, you know, almost as effective job as the anaglyphs of the 3D glasses. So for statistics, I'm just not kind of convinced that 3D graphics is the right thing. I mean, again, just because I'm not convinced doesn't mean it's a bad thing. I mean, I'm certainly wrong about things all the time, but you know, it's just not something I would work on. I mean, if I had an interesting student who was interested in it, I think that could be a fun project, thinking about how do you extend GGplot 2 to kind of 3D graphics. Or even more interesting, how do you kind of generalize it to ND graphics? Is I think something really interesting, but 3D, I'm sort of not convinced it's that useful. So if someone else wants to walk up for a question, I'll display an amusing graphic in the meantime. So this is the display isn't very good, but this is a tour that uses Chernov faces. Unfortunately, not changing very much, but hopefully you'd see them getting sadder and happier. But, so one thing that's interesting, I mean, just on this note, is that, you know, thinking about what the tour is, and when you're programming stuff in R, it's just so much easier to explore ideas than when you're programming in C. So even if R at some level is much, much slower than C, there's still a big advantage to using it because you can develop things much, much, much more quickly. And so that's really helped when we rewrite stuff that had been written in C. We can experiment with it, think about how do we break it up into these independent components.
What do you think Edward Tuff's books and things about that?
Yeah, I mean, Edward, you know, you can sort of hopefully tell a lot of GGplot 2 is developed as the aesthetics are really inspired by Tufte's work. But Tufte is basically a graphic designer and not a statistician. And even if you look at what his recent work is, I don't know if you've... You know, this is what Tufte is producing these days. So, you know, he has an so he has an absolutely fantastic sense of aesthetics, and reading his books with an eye to that, you know, how can I create beautiful graphics is really good. But he tends to be a bit on the minimalist side, so he creates things, I think that Tufte takes too many things away. So, you know, getting rid of grid lines altogether actually turns out to be a bad idea because grid lines actually help you compare curves. And his change to there's an interesting little paper. He had a proposal, one of his books, to modify the box plot in a way that kind of subtracts a whole lot of things away. But if you compare that to the traditional Tukey box plot, it actually it performs worse. So there's a sort of tension between creating beautiful things and creating useful things, and Tufte is, you know, always been more about creating beautiful things, and I think he's sort of going off the deep end a little bit in terms of beautiful things. You know, which is, you know, I think that's fine, and I think he just opened a gallery in Chelsea, so you can kind of see all the stuff in person now. But until you have to kind of take his advice with a grain of salt, I think, as with mine, of course. Yep.
Going back to the R and the web and GGplot, one thing I've encountered that would be extremely helpful would be, you know, when you render a plot, you render it to a device, either your screen, you know, X11 or whatever, or a file, right? But it's very difficult to actually, where I haven't found a way to actually render it to a socket, to a connection, so that I could easily, you know, tell send you're gonna render this, send it over there, and there's a server who knows, oh, grab it, okay, update the image that you're sending to the client. And you can get animations online that way, perhaps.
Yeah, I mean, I don't know, because I can show you. I mean, RStudio's figured out how to do it, so it must be possible. That's all I can say. So it might take a little. I don't know how many of you have seen RStudio. Yeah, okay, highly. I think there was a meetup about it a couple of weeks ago, right? So, I mean, they've clearly figured out how to do this stuff, how to send it over the wire. I mean, it just, you know, this is the thing that basically makes me think I could be fundamentally wrong about graphics on the web, because if you'd asked me whether this was possible, I would have said, no, there's no way you could do this. So, I mean, I just kind of, it continues to amaze me how quickly you can do this stuff and how fast you can kind of send bits over a wire. So really, and I think they have their little manipulate tool that lets you kind of do one very specific type of manipulation where you can drag stuff around and modify a plot. I mean, I think all these kind of little interactive things are useful, but I sort of want to aim, you know, what do we want in 10 years in the future? How can we really describe all the types of interactivity? But certainly, lots of this stuff is really interesting in the interim.
What do you think about building in protections about sort of getting the wrong kind of things? You're sort of iterating and creating all these different visualizations. Are there things that you can build in interactions to prevent kind of really going off the rails, or what do you think about that?
Yeah, I mean, one idea, sort of another way of thinking about where to go next with the grammar of graphics, I guess, I sort of think of it as like a poetry of graphics, right? So the grammar kind of says what can you say, but you really want to think about, you know, how do you say things effectively and, you know, beautifully. Maybe poetry is going a little bit too far again, but sort of thinking about that next level. Now we know what we can do. What should you do? And I think there's a lot of interesting stuff there in terms of kind of maybe can you suggest to the user, given that you've looked at this plot, what plot should you look at next? I mean, that sounds a little bit like Amazon, right? You've looked at these 3 books, maybe these 3 plots, maybe you want to look at this plot. But I think in terms of kind of thinking, you know, using some statistics, kind of running through some possible, these are where you might want to go next. Because, I mean, the other thing I haven't really talked about is in any real analysis, graphics aren't enough by themselves. You have to connect them into some modeling framework. And graphics are fantastic at revealing the unknown, but I mean, they're just so slow, right? If you've got 1,000 variables, you can't look at all the individual scatter plots. How do you figure out what are the interesting ones you should look at? And you sort of need something you need graphics so that you're not locked in too much, but you need modeling so you're steered in the right direction. And I think that getting that tension right is really, really important to sort of, you know, how do we lead people in the right direction without, you know, chaining them so they must go in this direction. And I think that's sort of all tied up with, you know, when you create a GUI to create plots, what should it do? How do you create a GUI, or how do you create a way of making plots that makes it easy but doesn't lock people into too many predefined choices? And, you know, certainly, you know, GGplot 2 is great if you're an analyst who's working with data every single day. But if it's something you're going to pick up and use every couple of weeks, you know, command line interfaces, you just kind of forget everything, and it's a very, very slow process. I guess. So I'll be hanging around for a while. Yeah, you're welcome to talk to me in person, or again, please feel free to send me an email, particularly about data analysis, or for me, if you need help spending your millions.